Okay, now that we've covered all the ideas of calculus, I want to do a few more things to kind of solidify it for you. And these are a couple problems that I've made up over the years. This very first one is one I thought of the very first time I taught calculus. And in fact, one of the students, after taking the final, said, "What a great problem this was." So it's one of those that maybe you love it or you hate it. So there's the parabola, f of x equals x squared. And here's what I'm after. I want to find the point C. Here's the point C right there, where the slope of the graph at that point is equal to the area under the graph from 0 to C. Okay? I want to find the spot C where the value of the slope is equal to the value of the area. Okay, so you see this is the problem that very quickly pulls together the two ideas of calculus right here in a single problem. So that's why I kind of like it. So let's do it. It's not hard. First of all, we want to find the slope there. How do you find the slope? Here's our function. You take the derivative. The derivative is, of course, 2x. And so at the point C, the derivative is going to be 2c. So there's the value of the derivative. Now, how do we find the area underneath the function from there to there? And of course the answer is we integrate it from 0 to c. And what do we have to do? Find the antiderivative. So that's going to be 1/3 x cubed from 0 to c. Stick in a c there, you're going to get 1/3 c cubed. Put in a 0, you get 0. So there's the value of the slope. There's the value of the area. We want to know when those two will be the same. So we set them equal to each other. Let's multiply by 3 to get rid of the fraction. Bring the 6c over, and you're going to get what? C cubed minus 6c is equal to 0. Factor a c out, and you're going to get c squared minus 6 is equal to 0. And so when will that be 0? It'll be 0 either when c is equal to 0, or the square root of 6, or the negative square root of 6. We're looking at just the positive x-axis here, so this would be the choice. What's interesting though is to notice that even if we include 0 here, that's not a place we would have thought of as being an answer, but it is an answer, right? At that point the slope is equal to 0 and the area from 0 to 0 is equal to 0. So that's why it's important at this point right here in the problem not to divide through by c. If we would have divided through by c right there and gotten c squared is equal to 6, we would have lost this as a solution. So that's why it's important in a situation like this to factor it and then divide out rather than just to divide through by your variable. When you divide through by a variable, you might be losing one of your options. This is the one we were looking for, but as I say, 0 is certainly a possibility as well. So so there you go. So there you are. That's kind of a nice problem. Let's do another one. This is a combination of two problems. And here's what I do. I start by saying you're going down the highway or moving along a line or something like this, and your position at time t is given by 3t squared plus 2t plus 1. This is your position. So if you were to graph it, I'm not going to graph it here, but it's some sort of graph where p of t is your position at time t. So here's the questions I want you to ask. I want to ask, how far traveled from t equals 0 to t equal 3. So what do? Well, we just take t of 3, or p of 3 rather. P of 3 is equal to what? 9 times 3 is 27. 27 plus 6 is 33. 33 plus 1 is 34. P of 0 is equal to what? Stick a 0 in here and you get 1. So how far did you travel? The distance you traveled was 34 minus 1 is equal to 33. There's how far you traveled in those 3 seconds. Second question. What was your average velocity? Okay, so the way to get your average velocity is to take your total distance divided by your total time. So it's going to be, I'll write it like this, p of 3 minus p of 0 all over 3 minus 0, which is 33 divided by 3, which is 11. So 11, whatever units we have, meters per second or whatever, that would be it. Next question. When were you traveling at the average speed? When travel at the average speed. Well, how do we get our instantaneous speed? We get our instantaneous speed by taking the derivative, so we know that v of t is equal to, the derivative of this is going to be 6t plus 2, and so we want to know, when will 6t plus 2 be equal to 11? When will that be equal to 11? So how do you do that? You solve it. You're going to get 6t is equal to, subtract 9, and you're going to get t is equal to 3 halves. Okay. Next question. What is velocity at t equal to 2? At t equal to 2. Well, here's your velocity at any time. So v of 2 is just going to be what? 2 times 6 is 12, plus 2 is, I'll do it like this, 6 times 2 plus 2 is going to be 14. And the last question is, what is acceleration at t equal to 2? And how do you find the acceleration? You take the derivative of the velocity and you get a of t is equal to 6. And so in particular, the acceleration at time 2 is equal to 6. Okay? So there they all are. And now let's just make sure you understand how those tie in with the graph here. Here's your graph. Here's t. P of t is going to be something roughly like this. Let's see, at time equal to 0, it starts at 1. It's going to be somehow increasing. It maybe looks just roughly like that. And how far did you travel from time equal to 0 to time equal to 3? Here's 3 right there. There's P of 3 right there. So the distance from here to here is how far you traveled. What was your average velocity? Well, think about what we did there. If you take the distance you travel, there's the distance you travel, divided by your time, you're taking this divided by this, you're finding the slope of this line. So this is basically your mean value theorem for derivatives right here, right? You're finding the average slope right there. The average slope was 11. When did you travel at the average speed? Well, there's your mean value theorem again. What's the mean value theorem say? It says whatever this average slope is, it has to occur someplace in between here. So here's a spot right there. There's a spot right there, namely at 3 halves. If I had drawn it nicely. That would be 3/2 right there. That's the spot where the slope is equal to 11. That's the spot where the instantaneous slope is equal to 11. So there's the spot where you're going your average. That's the one time when you're going the average speed. Otherwise, you're going faster than you're going slower than the average speed here, and you go a little bit faster than the average speed here. What's the velocity at time equal to 2? Well, you stick a 2 in here and you find the slope there, and that gives you the slope at 2. And then finally the acceleration, that would be the slope of the slope, or the concavity actually. So there's that. Okay, so the point is this all uses the mean value theorem for derivatives with this problem. Now we're going to keep all the questions the same, and we're going to keep the function the same, but now instead of this being p of t, this is going to be the velocity. So now the function that we have is no longer the position, it's the velocity at time t. How is that going to change things? Okay, that's why I like this. It really makes you think through all these things we've learned throughout the course. How far did you travel from time 0 to time 3? Okay, well, what we have now is a graph of the velocity, and if you want to find the distance from the velocity, you need to integrate it. So now, in order to answer this question, we need to actually integrate from 0 to 3 this function, 3t squared plus 2t plus 1 dt. See if I have room to do it all. The antiderivative is going to be t cubed plus t squared plus t. That turned out nicely. I guess that's why I chose what I did. From 0 to 3, if you put a 3 in here, you're going to get 27. 27 plus 9 is 36. 37, 38, 39. So you're going to get 39. Put a 0 in here, you get 0. So there's your answer. Okay? So there's the answer to that one. What was your average velocity? Well, the average velocity, same as before, is what you get by taking your total distance. So it's going to be 39. There's your distance you traveled, divided by your time, which is 3, and so your average speed is going to be 13. Okay, there's your average velocity. When did you travel at the average speed? Well, that one's easy now. We don't have to take the derivative. There's our velocity right there. So we take our velocity and we take 3t squared plus 2t plus 1, and we set that equal to 13. This is the only one that gets a little bit messy. And let's go ahead and do as much as we can here. We're going to get 3t squared plus 2t. If you subtract 13 from both sides, you're going to get minus 12 is equal to 0. Subtract 13 from both sides. And so now, in order to find out the value of t that makes that 0, you need to use a quadratic formula. So t is going to be negative 2 plus or minus the square root of 2 squared is 4 minus 4ac. So it's going to be plus 4 times 3 times 12 all over 2 times 3 is 6. Okay, and just for sake of space and so on, I'm not going to go further on that, but basically this is going to be, well, here, maybe I can go one step further. Negative 2 plus or minus, this is 144, 148, square root of that, all over 6, and you can figure that out. Simplify it a little bit more. What is the velocity at time equal to 2? Well, that's easy enough. All we do is stick a 2 into the velocity, so that's going to be 3 times 2 squared plus 2 times 2 plus 1, which is what? 4 times 3 is 12. 12 and 4 is 16, plus 1 is 17, if I'm doing this right. And finally, what's the acceleration? Well, to get the acceleration, we need to take the derivative of the velocity again. So the acceleration at any time is going to be what? 6t plus 2? 6t plus 2. So the acceleration at time equal to 2 is going to be what? Put a 2 in here, you're going to get 12 plus 2 is 14. Okay, so again, let's see once what this all amounts to with regard to this graph. How far did you travel? This is the graph of the velocity, so what we were doing was we were finding the area underneath this graph. The area underneath this graph gave us how far we traveled. That area was 39. Okay? What was your average velocity? Well, what did we do? This thing gave us the velocity at any time, and we want to find the average velocity, so we took this area and we said, what, instead of the height of the velocity going from here to here, what if the height were uniform all the way across? Do you see what we were doing? So we were basically, just like that anthill, we were shaking it flat. We were shaking it flat so that all this stuff went right in there, and we said if we take this total area and we divide it by, this is 3, this is 0, we divide it by 3, we're going to find this average velocity. It started velocity here, it ended up here. We want to know if you were to shake it flat and go at the same velocity the whole time, what velocity would you have had to go at? And so you take this whole thing, divide it by 3, and what did we end up with? 13. So that was your average height. See, so that's the mean value theorem for integrals right there. See that? When did you travel at the average speed? Well, here's your average speed. When did we travel at it? It was right there at whatever this number is. Call that C, right there at C. Okay? What's the velocity at time equal to 2? Well, I'm not sure where 2 was on here now, but say 2 is right there. If 2 is right there, all you do is you find the height right there, and there you have velocity at 2. And what's the acceleration at time equal to 2? Well, since this is the velocity, the derivative of the velocity gives the acceleration. So now all we are asking is, what's the slope there? What's the slope at that point? Okay, so these two problems really capture just the guts of the course as far as integrals and derivatives and the mean value theorem, both of the mean value theorems. Really nice. If you understand these, you really have the idea of the course right there. Okay, very good. So that's the one thing, second thing I wanted to do. And the third thing I wanted to do is revisit the logarithm. Remember, that was the one thing that when we gave it to you before, we mentioned what the exponential function was. It looked like this. And here's the logarithmic function, y equals e to the x, y equals ln of x. And instead of actually proving to you what the derivatives of those were, we just got a table and used the table to kind of convince us. I want to revisit this now because now we can do it more rigorously, okay? And it'll be good review for you as well. The ln, here's the definition of the ln. The ln of x is defined to be the integral from 1 to x of 1 over t dt. That's the definition. That's really how you define it to begin with. In a lot of the older calculus books, you never even saw the logarithm and the exponential until after you talked about the integral and the fundamental theorem of calculus. And then that's when you define it. And because of the fact that we want to have calc books that people can use for engineering courses, they want people to see it early on so that they can use the things in your engineering courses. So they kind of have reshuffled the topics. But this is the more rigorous way to do it, is to not even mention this until this point in the course. So let's see. Let's just notice what's true of the ln given this definition. First of all, by definition, the derivative, by the fundamental theorem of calculus, the derivative of this thing is the value of the function. The derivative of the ln of x is just f of x, which in this case is going to be 1 over x. There's the derivative right there. And notice, what else can we notice? Notice that this thing is 1 over x. Well, first of all, notice that, that there's so much neat stuff here. Here's what the function 1 over x looks like. And we're finding the area from one either to the left or the right. Notice that if you go from 1 to the right, you're going to be accumulating positive area there. See that? If you go from 1 to the left, what happens? From 1 to the left, this is a positive quantity, but you're going from right to left, and so this is a negative. The value of the integral is going to be negative. See that? So that's why the logarithm, if you were to graph it at 1, from 1 to 1, the value of the logarithm is 0. But if you go to the right, it becomes positive. If you go to the left, it becomes negative. And as far as it can go is 0, because there you have a discontinuity in this function. Okay, so all the properties of the logarithm come just from this. Okay. I don't want to take time to go into all of them, but let's just look at the most important property of the logarithm. If we take the derivative of the ln of a times x, then by the chain rule, what's that going to be? It's going to be 1 over ax times the derivative of ax. The derivative of ax is a, and so notice that reduces to 1 over x. So notice that the derivative of this and the derivative of this are the same, and if the derivative of two functions are the same, that means that those two functions vary by a constant, right? If the derivatives are the same, that means that they vary only by a constant. And to find out what that constant is, all you have to do is to stick a 1 in for x. If you stick a 1 in for x, you get the ln of a here. The ln of 1 is equal to 0 plus c. So that tells us that c is equal to the ln of a. So c is equal to the ln of a. And there, right there, look at there, we've got the proof that the ln of the product of two things is the ln of the first plus the ln of the second. Okay, so that's one of those most important properties of the ln. So I want to just show you that. The last thing I want to show you, we already now have a rigorous reason for seeing that the derivative of the ln is equal to this. Let's do one more thing. We know by definition that the e to the x is the inverse of the ln of x. Okay, so the ln of e to the x is equal to x. They undo each other. Agreed? They undo each other because they're the inverse functions. And now we can take the derivative of both sides. If we take the derivative of both sides, the derivative, let's go ahead and do it. I'll do one more step for it here. The derivative of the ln of e to the x is equal to the derivative of x. What's the derivative of the ln of anything? It's 1 over that thing times the derivative of this thing. Now realize we're not assuming we know the derivative of e to the x now. We're going to find it. Okay, so the derivative of the ln of anything is 1 over that thing times the derivative of the inside is equal to the derivative of this side. Well, the derivative of x is just 1. And now we can solve for this by multiplying through by e to the x. Look what we get. The derivative of e to the x is equal to e to the x. So there you go. So there's kind of that core stuff that I wasn't able to show you rigorously before, but there's the rigorous proof of this. And again, it shows you why the ln has the behavior it does. It's going to be increasing as this increases. And there you go. I guess, doggone it, I'm going to show you just one more thing. This is so cool. This gets into Calc 2 a little bit, but I'm going to show you one more thing. How high does this thing increase? Basically, what we're asking is, as you go out to infinity, how much area is there underneath 1 over x as you go out farther and farther? Because that's going to be how high this increases. The height of this is equal to the area underneath this function. So let's just look at it for a second. This is very, very cool. Here you have the function 1 over x. Here you have 1. There you have 2, 3, 4, 5, 6, 7, 8, and so on. So we're interested in how much area is there underneath here. And here's what I want you to notice. What if we make a whole bunch of little rectangles? Go back to our rectangles underneath this thing again. Okay? What are the areas of these rectangles? This height is 1/2. This is 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, and so on. So the areas of these rectangles are going to be 1/2 times 1, 1/3 times 1, 1/4 times 1, 1/4 up, 1, so all the widths are 1, plus 1/4, plus 1/5, plus 1/6, plus 1/7, plus 1/8, plus 1/9. I'm going to go out to 1/16, all the way to 1/32, and keep going. And here's what I want to show you. This is really cool. This gets into stuff that you see in Calc 2. If you were to add up all these numbers, do all those numbers, do they end up getting close to some finite number? Like if you took 1/2 plus 1/4 plus 1/8, like a pi, a half of a pi plus a fourth of a pi plus an eighth of a pi plus a 16th, all those numbers are going to add up to 1 because you end up with 1 pi by the time you're done. But look at these numbers. Here you have a 1/2. A third and a fourth is bigger than a fourth and a fourth. Agreed? A third and a fourth is bigger than a fourth and a fourth, and a fourth and a fourth is another 1/2. So this is bigger than 1/2 right here. Now you grab the next 4 of these. You ended up with 1/8. If you had an eighth plus an eighth plus an eighth plus an eighth, that would be a 4/8, which is a half. You've got something bigger than a half here. See that? Now you grab the next 8 of them. If they were all 1/16, you would have 8/16, which is a half. You've got things bigger than 1/16 here, so this is going to add up to be bigger than 1/2. And you keep taking chunks that are twice the size like that, and you can keep getting chunks that are bigger than 1/2. So the point is, as you go out to infinity here, you can get as many of these chunks as you want, all bigger than 1/2. And so the area of all those things together can get as big as you want it to get, which means that the area underneath this graph gets as big as you want it to get. So that area underneath that graph goes to infinity, which means that the ln curve, as you go up this way, it never levels off. It just keeps going up, goes up to infinity, which is a very important aspect of the ln curve, which is again something that we mentioned before but never proved. So there you proved it. And obviously, just to finish it here, the limit of the ln of x as x goes to 0 from the right obviously heads down to minus infinity. Okay, so there you go. Okay, cool stuff. So when I say obviously, there's a symmetry there. So I'm going to do one more lecture on just a couple review problems, but this is really all the material right there. So stop right here if you want, or if you want a few more review, look at the next lecture. Very good.